Picture this for a moment. You're standing on the night side of Earth, the sky ink black and quiet, and somewhere out beyond the planets, a stranger is sliding toward the sun. You can't see it with your eyes, not yet. But the instruments can. They're already picking up the faint breath of an interstellar object that isn't from here. December 19th, 2025. Keep that date in your mind. On that day, 3I Atlas, an interstellar visitor, will sweep through the inner solar system, passing close enough that its outflow and dust could intersect Earth's neighbourhood. This is only the third confirmed object we've ever seen arrive from another star. That alone would be enough to make astronomers lean forward. But 3I Atlas is doing something that feels off. Let's start with what we know. As it falls toward the sun, 3I Atlas is warming and venting material the way comets do. Those gases spread into a thin expanding cloud called a coma, and the pressure of sunlight and solar wind drags some of that cloud into a tail. Normally, when we measure what's coming off a comet, we see a chemical personality that makes sense for frozen rock that's been sitting in deep space for billions of years. Here the personality is weirdly split. In the coma of 3I Atlas, telescopes have picked up strong signals from methanol, CH3, and from hydrogen cyanide, HCN. Methanol is a simple alcohol. It's common in space, and in the right environments it can be a stepping stone toward more complicated organic molecules. Hydrogen cyanide is a different kind of guest. On Earth, it's infamous, because in high concentrations it blocks cellular respiration. In other words, it stops cells from using oxygen to make energy. So one molecule whispers biochemistry, while the other carries a cold warning label. That contrast is the core riddle. It's a bit like finding a carefully stocked pantry next to a shelf of cleaning solvents. Either you're looking at a normal household with unfortunate storage habits, or you're looking at something else entirely. So what this means is we have to be cautious about narrative. The same chemistry can look nurturing in one context and lethal in another. Harvard astrophysicist Avi Loeb has pushed this question into the spotlight. Is 3I Atlas purely natural, or could it be engineered, or even a hybrid of both? He's not saying aliens did it as a slogan. He's asking whether the data fit what a normal interstellar comet should do. And right now, some pieces don't line up cleanly. Here's one of the stranger pieces. Observations with ALMA, the Atacama, large millimeter, just sub-millimeter. Array and Chililet scientists map where the methanol is coming from inside the coma. ALMA doesn't just tell you methanol is there, it can show you the structure of the outflow almost like a thermal camera for molecules. What it found was unexpectedly symmetric. The methanol wasn't spraying out in a chaotic patchwork. It looked organised, as if it were emerging from two main regions on opposite sides of the nucleus. That leads to a very specific physical picture. Imagine the nucleus of 3I Atlas as a rough rotating body with two dominant vents, like valves. In one scenario, those vents are simply patches of surface rich in methanol ice. As sunlight hits them, they sublimate, turning from solid to gas and feed the coma. If that's the explanation, then 3I Atlas is a natural object with a lopsided internal chemistry, not so different from some comets we've seen at home. But there's another possibility. The methanol might not be coming directly from methanol ice. It could be produced by some kind of chemical processing, either on the surface or in the coma itself. Think of it like steam rising from a pot, not because the pot contains water, but because something inside is being broken down into water as it heats. If that's happening here, then the symmetry might reflect a chemical factory rather than a simple patch of ice. And then there's the most provocative option, that the structure is engineered. If a spacecraft or an interstellar warship, Star Wars-like in its overall silhouette but vastly more advanced, were venting propellant or dumping material, you might expect coherent symmetric outflows. In other words, the two-valve look is not impossible to reconcile with technology. It's just an extraordinary claim, and extraordinary claims need extraordinary evidence. So what evidence do we actually have? Methanol and HCN are both common cometary species. We've detected each of them in many solar system comets. What's striking here is the ratio and the behaviour with distance. In 3I Atlas, methanol appears unusually abundant and its brightness rises rapidly as the object approaches the sun. That suggests either a large reservoir of methanol or a process that's making methanol more efficiently than expected. In other words, something is enhancing the methanol signal. There are a few natural ways to do that. First, 3I Atlas could have formed in a region of its home system where methanol ice was especially plentiful, then preserved that inventory during eons of interstellar travel. Second, the methanol could be trapped in Clathrate's ice cages that release their cargo in bursts when heated, producing strong spikes. Third, sunlight could be driving chemical reactions on the surface that generate methanol at a surprising rate, almost like a runaway catalytic effect. Notice the pattern. Each natural explanation requires a specific set of conditions, but none of them violates physics. They're like 3 different paths through a forest, all plausible, none guaranteed. Now bring hydrogen cyanide back into the frame. HCN can be a building block in prebiotic chemistry. In lab settings, it participates in pathways that lead toward nucleobases, the letters of RNA and DNA. But it's also toxic if delivered in high dose, so the presence of HCN doesn't tell us life or death by itself. It tells us reactive chemistry. The question is, what kind of system produces both high methanol and significant HCN while maintaining such organized outflow? This is where the story starts to feel like a slow-moving test. 3I Atlas is arriving from somewhere we can't see, carrying a chemical signature we're still learning to interpret. If it's natural, it could teach us about how other solar systems seed organic molecules. If it's not, then it would be the first tangible hint that something else is roaming the dark between stars. Either way, we're not guessing in a vacuum. The weeks leading up to December 19th are packed with follow-up observations. Spectroscopy in the coming months will refine the ratios, map more molecules, and watch how the vents evolve. The data will either settle into a familiar comet pattern, or they'll keep resisting our expectations. And that's the quiet tension hanging over this object. The closer it gets, the more it reveals, but every reveal seems to raise a new question. If the methanol vents are real, valves, what drives their symmetry? If methanol is being produced rather than merely released, what chemistry is doing the work? And why does this interstellar visitor look, at least for now, like it's following rules we only half recognize? So what this means is we're staring at a faint trail of clues and trying to decide whether we're seeing an exotic kind of comet or the exhaust of something built. The difference matters, but the universe doesn't volunteer answers quickly. It makes you earn them, one spectrum at a time. Picture this for a moment. You're hovering above the solar system like a quiet observer, watching the planets glide in their lanes. Earth is a bright bead on a thin, invisible ring, and cutting across that ring at a slant is 3I Atlas, racing through on a hyperbolic path fast enough that after this pass it will never be bound to the sun again. Closest approach to Earth happens on December the 19th, 2025. The numbers sound reassuring on paper, about 1.8 astronomical units, roughly 270 million kilometers. NASA and the European Space Agency have been clear about the obvious point. There will be no impact. 3I Atlas is not going to hit us. Its trajectory is well understood and the math is solid. But impact is not the only way a passing object can matter. Distance alone can lull you into the idea of safety because distance is easy to visualize. Geometry is not. And geometry is the real story of December 19th. Imagine Earth as a marble and 3I Atlas as a truck blasting past on a highway. The truck doesn't swerve into you. It doesn't even come close. But it is leaking a fine mist out the back. If you're standing downwind when it passes, you still breathe some of that mist. Now scale that up to astronomical units, replace air with solar wind, and replace normal mist with charged dust and reactive molecules. The question isn't, will 3I Atlas crash into us? The question is, will Earth intersect any part of the chemical wake it is leaving behind? Most of the diagrams you see online flatten this into 2 dimensions, like a coin sliding across a table. In reality, the orbital geometry is 3-dimensional. 3I Atlas is tilted relative to Earth's orbital plane. Picture 2 highways crossing but at different elevations. The vehicles don't collide because they're not in the same sheet. That's the reassuring part. The less reassuring part is that the wake is not a thin line glued to the object's path. It's a cone, more like a spreading plume, of gas and dust expanding outward as 3I Atlas moves. And that plume is being pushed and sculpted by forces that don't care about our comforting flat diagrams. The solar wind constantly blows outward from the sun, a stream of charged particles that is structured into faster and slower lanes. Threaded through that wind is the interplanetary magnetic field. If the wake of 3I Atlas couples to that field, if any part of it becomes charged, then pieces of the wake can drift far from the object's geometric trajectory. So what this means is the track on a chart is not the whole footprint in space. ALMA has already shown that the venting is directional. Hydrogen cyanide is depleted on the sunward side and enhanced elsewhere, while methanol shows the opposite pattern, stronger in some directions, weaker in others. That sunward symmetry tells us the outflow isn't random, it's like a sprinkler that only turns on in certain arcs. The jets are pointed somewhere, and here's the quiet hook in the middle of all this. If the jets are pointed, then which sector is Earth going to pass through? The methanol-rich sector, the cyanide-rich sector, or some mixture we haven't tasted before? To understand why that matters, we have to talk about dust you can barely call dust. The wake contains charged nanograins, particles so small they're almost molecular. When grains like that pick up electrical charge, they stop behaving like little cannonballs. They start behaving like tiny rafts on invisible rivers. The rivers are magnetic field lines. They curve, twist, and sometimes form filamentary channels that can ferry particles across distances that gravity alone wouldn't predict. We've seen an Earth-scale version of this. A volcano erupts, and its ash doesn't spread evenly like a neat classroom diagram. Instead, high-altitude winds catch it, thread it through jets and eddies, and carry it thousands of kilometers downwind. Space is different in temperature and density, but the principle is the same. Plasma flows can build structure, and structure can guide matter. Now let's put some rough numbers on the dilution question, because it's easy to feel dread without checking scale. If 3I Atlas is releasing methanol and hydrogen cyanide at the rates ALMA measured, and those molecules expand outward into a roughly spherical shell, then by the time that shell reaches Earth's orbital distance, the average concentration drops by about a factor of 1 trillion. 1 trillion. That's cosmic dilution. In other words, spread out evenly, this wake becomes so thin that it is functionally irrelevant to life on Earth. To reach lethal hydrogen cyanide concentrations in Earth's atmosphere, the object would need to release amounts orders of magnitude higher than anything observed, so the mainstream position is reasonable. Dilution kills the danger. But here comes the big but, and it's the kind that makes scientists stay awake even when they want to be done. That dilution argument assumes uniform dispersion. It assumes the wake spreads evenly in all directions and never gets focused. Yet we know focusing happens in plasmas. A coronal mass ejection, if it erupts in mid-December, and if its field geometry lines up just right with Earth's magnetosphere at the same time 3I Atlas passes, could nudge a narrow filament of charged dust and gas in our direction. I'm not saying this will happen, I'm saying it's physically allowed. ALMA's spectra show preferred velocities, certain Doppler shifts stronger than others, meaning the molecules are already leaving the nucleus preferentially in specific directions. The trouble is, ALMA maps only the near field, within a few 100,000 kilometers. It can't see the full heliospheric wake stretching millions of kilometers downstream. So what this means is we're standing on a shoreline, measuring the first ripples, while the ocean beyond stays dark. Solar activity is unpredictable on short timescales. The interplanetary magnetic field can tilt, kink, and reconnect. If the wake intersects one of those structured lanes, it could be shepherded along it like dust in a magnetic pipe. Uncharged molecules such as methanol wouldn't feel the field directly, but they can stick to charged grains or get dragged along through collisions. The result is anisotropic dispersion, not a perfect sphere, but a smeared lopsided cloud with a few brighter threads. So December 19th is more than a date. It's a geometric event. It's the moment Earth's orbit cuts through the projected zone where 3I Atlas's wake might be drifting. Whether anything reaches us depends on variables we can't fully lock down yet. Solar wind speed, magnetic field orientation, the exact release rates and velocity distributions of the molecules, and how strongly the dust is charged. There's a calm way to hear that, and a tense way. The calm way is, the most likely outcome is nothing noticeable at all. The tense way is, nature has pathways for delivering material across vast distances, and we don't get to choose whether this wake finds one. In other words, it's not just about how far away the object is, it's about how the space between us is wired. Either way, we are flying partially blind. And that's why the chemistry in the wake matters so much. Because if any fraction of it does thread toward Earth, Even temporarily, it's not just dust. It's a cocktail carrying two very different stories in the same breath. In the next part, we're going to step out of geometry and into meaning. We'll ask what methanol and hydrogen cyanide imply when they ride together, how the same data can sketch a friendly gardener or a serial killer, and why both interpretations are uncomfortably hard to dismiss. Picture this for a moment. You're sitting in a dim control room before dawn, the kind that smells faintly of coffee and electronics. On the main screen, a spectrum glows like a barcode made of starlight. Each spike is a molecule announcing itself from millions of kilometers away. You're not looking at a photograph anymore. You're listening to a chemical voice, methanol and hydrogen cyanide. Those two signals keep coming back, and together they create a kind of moral illusion. The same data can feel gentle or threatening depending on how you let your mind frame it. Avi Loeb described this contrast with a line that stuck because it's so human. One interpretation is a friendly gardener, the other is a serial killer. He's not saying either is true, he's pointing out how wide the interpretive gap still is. Let's walk slowly through both frames, because the difference between them is not in the molecules themselves, it's in dose, context, and intent. And intent is the one thing the universe never labels for us. Start with the gardener. Methanol is a basic, widely available organic compound in space. In cold interstellar clouds, methanol forms on dust grains through hydrogenation of carbon monoxide, and it can ride inside ices for extremely long times. When that methanol is released near a star, it becomes part of a chemical network that can generate more complex organics. In some models of prebiotic chemistry, methanol can help build aldehydes, sugars, and other intermediates. So if you see a comet bringing methanol into a young planetary system, you could see it as raw material, a kind of starter kit. Now layer on hydrogen cyanide in the same gardener frame. HCN is dangerous in a living room, but powerful in a lab. It's one of the classic precursors in pathways toward nuclear bases. In other words, it can be part of the road to RNA. So what this means is that a cocktail of methanol plus HCN might be the kind of dirty chemistry that naturally nudges lifeless worlds toward complexity. It wouldn't be a clear act of seeding, more like the universe leaving useful ingredients on the counter. This is a very old idea, really. Interstellar objects could be couriers of chemistry. Their home systems forge certain molecular ratios, then time and cold preserve them. They drift for ages through space, and sometimes they pass through another system and shed those molecules into it. If 3I Atlas is that kind of courier, then its strange chemistry could be telling us about an exotic birthplace, not about intention. But now step into the serial killer frame and feel how the same facts twist. Hydrogen cyanide is lethal because it binds to cytochrome C oxidase, shutting down the final step of cellular respiration. A few hundred parts per million in air can kill humans quickly. That's the everyday translation. HCN is a suffocation switch for biology. Methanol can also be toxic on Earth because it metabolizes into formaldehyde and formic acid, damaging nerves and organs. Again, dose matters. But in the serial killer story, you're not focusing on small traces, you're focusing on delivery. Here's the uncomfortable hinge. If an object were engineered to alter a biosphere, you wouldn't need to deliver oceans of poison. You'd need to deliver it in focused, timed bursts into specific layers of atmosphere or onto specific regions of terrain. A high-altitude filament of HCN-bearing dust, funneled along magnetic channels, is not the most likely thing in nature, but it's the kind of delivery mode that makes the serial killer story feel less like science fiction and more like a remote physical possibility. That said, the data we have right now do not show anything like a targeted assault. We see a comet-like coma released in jets, expanding and diluting. The odds strongly favour harmlessness, so why does the serial killer story linger at all? Because the behaviour of the chemicals is more extreme than expected. The methanol abundance is high, and its increase toward the sun is steep. Hydrogen cyanide shows a different spatial pattern, depleted sunward, enhanced elsewhere. In other words, the syrup and the solvent are not just mixed, they're segregated in a way that implies some internal structure. The Gardner story says, internal heterogeneity in a natural body, maybe layered ices, maybe distinct patches. The serial killer story says, separate reservoirs or separate functions. Both stories are interpreting a single observation, organisation. And organisation is slippery. Nature can be organised without intention, Snowflakes are organised. Crystal lattices are organised. Even comet jets can be organised if the nucleus has a certain rotation and thermal layout. So what this means is that symmetry or structure doesn't by itself imply design. It only implies that something is controlling the flow. To decide what kind of control we're seeing, we have to test natural hypotheses hard before we even glance at extraordinary ones. The text lays out 3 natural routes that can produce the chemistry we're watching. The first is a methanol-rich birthplace. Some protoplanetary disks, depending on temperature and radiation environment, allow methanol to build up to large fractions of ice. If 3I Atlas formed in one of those disks, its nucleus could hold an unusually big methanol inventory. HCN could be a co-traveller, also enhanced depending on local nitrogen chemistry. In that case, the object is strange only because its home system was strange. The second natural route is clathrate trapping. Think of clathrates as ice cages. They can lock volatile molecules inside a water-ice matrix. When heated, clathrates don't slowly seep, they pop. They release trapped gases in sudden bursts. That could create sharp increases in methanol output as 3I Atlas approaches the Sun, even if the bulk methanol fraction is not absurdly high. In other words, it's the packaging that makes the signal dramatic. The third route is surface chemistry under sunlight. When ultraviolet radiation hits icy mixtures, it can break apart simple molecules and reassemble them into others. If the surface of 3I Atlas is rich in CO, CO2, and hydrogen-bearing species, UV-driven chemistry could generate methanol at a higher than normal rate as the object warms. That would also fit a steep distance dependence. It's like a snowbank that starts to emit a scent only when the first sunlight hits it. Not because the scent was stored there, but because the light activates a reaction. Each of these explanations is conservative. Each keeps us in the natural box. The problem is not that they're weak. The problem is that we don't yet have enough constraints to choose among them. And that uncertainty leaves a space where more exotic interpretations can echo. Avi Loeb's role here is partly psychological. He's resisting the urge to treat interstellar objects as just comets with a passport. He's saying, if something is odd, we should be willing to admit oddness and follow it wherever it goes. That doesn't mean jumping to aliens. It means not sanding the data down until it fits what we expect. So where are we right now between Gardner and serial killer? We're in the middle. We have a chemical inventory and a spatial pattern that can be explained naturally, but with some effort. We have no smoking gun for design. Yet we also have a visitor from another star whose behaviour is not perfectly ordinary, by our local standards. In other words, 3I Atlas is a mirror. It reflects our assumptions about what nature should look like. Sometimes nature surprises us. Sometimes it forces us to expand the range of normal. The only way to know which is happening here is to keep watching. As December 19th approaches, more spectra will come in. Other molecules may reveal themselves. Isotopic ratios might point to a specific kind of stellar nursery. And the jets themselves may change or fade, telling us whether the 2-valve picture was a temporary thermal feature or something deeper. But there's another reason this moment matters. If interstellar couriers like 3I Atlas are common, then the chemistry they carry is one of the great quiet engines of cosmic evolution. It's how star systems talk to each other without ever meeting. And if, in rare cases, some of those couriers are not natural, then chemistry becomes not just a messenger, but a language. We're not at the language stage yet. We're still learning the alphabet. We're at that slow, careful phase where every spike in a spectrum can be either a mundane molecule or a door. And there's a door we haven't opened in this story yet. In the next part, we're going to ask why a body like 3I Atlas might aim for icy moons instead of Earth, why Europa enters this conversation at all, and what kind of trajectory would make that choice practical. Picture this for a moment. You're drifting outward past Mars, past the asteroid belt, into the colder lanes where sunlight feels thin and distant. Ahead, Jupiter hangs like a pale lantern, and around it spin small worlds sealed in ice. From here, Earth looks less like a destination and more like a crowded shoreline already busy, already loud. We've been talking as if Earth is the obvious focus of December 19th. That's natural, it's where we live. But the universe doesn't rank targets by our comfort. So let's ask a quieter question, one that shifts the whole frame. What if 3I Atlas isn't aiming at us at all? If you were an interstellar carrier, natural or not, and your purpose was to spread chemistry, or even life, Earth wouldn't necessarily be the most interesting place in this system. Earth is already occupied. Every niche is taken by organisms that have had billions of years to dig in, diversify and defend their turf. Dropping new biology into that kind of ecosystem is like trying to plant a sapling in the middle of an ancient forest. Most of the time, the forest wins. An icy moon is different. An icy moon is a blank slate. Take Europa. Jupiter's fourth largest moon wears a shell of water ice that hides a global ocean beneath it. By volume, that ocean is roughly twice the total volume of all Earth's oceans combined. It stays liquid not because Europa is warm, but because Jupiter squeezes it. As Europa orbits, tidal forces flex the moon's interior, generating heat the way a paperclip heats when you bend it back and forth. The surface is frozen and blasted by radiation, but underneath is liquid water, dissolved minerals, and possibly hydrothermal vents. In other words, Europa has three things that matter if you're thinking about biology: water, energy, and chemical gradients. The gradients are crucial. Life doesn't need sunlight if it can harvest energy from chemistry. On Earth, entire ecosystems thrive around deep-sea hydrothermal vents, powered by chemosynthesis. No photosynthesis, no daytime, just chemistry feeding chemistry. Europa could host something similar. Now add methanol to that environment. Under high pressure, low temperature, and continuous radiation from Jupiter's magnetosphere, methanol can act as a carbon source and an energy source for chemosynthetic systems. It's fuel that doesn't require light. It's also a flexible precursor, a molecule that can be nudged into more complicated organics under the right conditions. So if an interstellar object were shedding methanol-rich material, Europa is one of the places where that material might matter most. And Europa isn't alone. Enceladus, Saturn's small moon, also hides an ocean under ice, venting plumes through cracks at its south pole. Other icy bodies, Ganymede, Callisto, Titan, each offer different combinations of water, energy, and protected chemistry. If you wanted to seed an ecosystem somewhere protected, somewhere that isn't already saturated with life, those worlds make more sense than Earth. So what this means is that Earth might not be the prize, Earth might be the hallway, but could 3i Atlas even reach a place like Europa? This is where orbital mechanics steps in, and it turns out to be less far-fetched than you might think. 3i Atlas is on a hyperbolic trajectory. It's coming in fast, swinging through the inner solar system, and then, unless something changes, it will escape forever. That makes it sound like a one-shot flyby. But hyperbolic paths can still be nudged. If the velocity and direction are right, small adjustments along the way can bend a future track toward the outer planets. Engineers talk about delta V. That's the change in velocity needed to alter a trajectory. In spaceflight, delta V is currency. The less you need, the more plausible your plan. If an object like 3i Atlas could make even modest course corrections, it might thread its way toward Jupiter's neighbourhood without spending a fortune in that currency. And space offers discounts. A gravitational assist using the gravity of a planet like Earth or Mars can reshape a trajectory for free, in the sense that you gain or lose heliocentric energy without burning propellant. We do this routinely with spacecraft. Voyager did it, Cassini did it, New Horizons did it. A well-timed slingshot can change where you end up. This is speculative, yes, but it's not physically absurd. The door is open, in principle. Now let's widen the speculation slightly but keep our feet on the ground. There's an eerie interpretation of December 19th that isn't about payload delivery at all. It's about assessment. What if the close pass by Earth is a scan? If 3i Atlas, or a mechanism controlling it, were capable of sensing, then a flyby like this would be a chance to sample Earth's habitability without committing to anything. Think of it like an animal sniffing the air before stepping into a new valley. You don't move in until you know whether the place is hospitable. What would an advanced probe look for? The same things we look for when we search exoplanets. Atmospheric composition is first. Oxygen and methane in the same atmosphere is a powerful biosignature because they destroy each other. If you see both together, something has to be continuously replenishing them. Ozone is another clue because it forms from oxygen, hinting at photosynthesis. Add to that surface temperature patterns, albedo cycles, seasonal variability, and signs of liquid water. Then there's the electromagnetic world. Radio emissions, modulated signals, artificial spectra, anything that suggests the presence of technology. Not because technology is required for life, but because a technological biosphere is hard to miss once you know how to listen. So what this means is that a close pass could be reconnaissance. If Earth looks biochemically occupied in a robust way, maybe you don't bother inserting material here. Maybe you aim for a quieter ocean under ice instead. But before this idea sweeps you away, let's anchor it to the counterpoints, because they're substantial. Targeting an icy moon is not easy. You need to know where that moon will be when you arrive years later. You need to match velocity vectors. You need propulsion and navigation, and some onboard computation or pre-programming. Even small course corrections at interstellar speeds require significant delta V. And right now we haven't seen evidence of large-scale propulsion events from 3I Atlas. We see venting of molecules. We do not see clear non-gravitational accelerations. We do not see trajectory deviations that scream controlled thrust. The object appears to be following its hyperbolic orbit like a fast, tumbling natural body. So the sober view is, if 3I Atlas intersects Europa's gravitational sphere of influence later, it may be coincidence. Random intersections are low probability, but not zero. We've seen interstellar visitors twice already, and statistics suggest we'll see more. A rare geometry can happen by chance. Still, the tension remains because the object doesn't look entirely random in other ways. The directional asymmetries, the unusual molecular ratios, the steep distance dependence of methanol production, these are the kinds of things that keep the alternative stories alive, not because they prove design, but because they resist simple, ordinary comet expectations. Here's how science can test this without drifting into mythology. If 3I Atlas changes its venting pattern after planetary flybys, if jets intensify or weaken in a way that doesn't correlate with solar distance or rotation, that would be interesting. If fragments or secondary objects split from the main body and trend toward Jupiter, that would be extraordinary. If we detect consistent non-gravitational accelerations aligned with deliberate steering, that would be hard to ignore. But for now, we're at the edge of a decision tree with more branches than answers. Earth might be a bystander, Europa might be the real stage, or neither might matter at all to a purely natural wanderer that just happens to be chemically dramatic. And suspended between those options is another possibility, one that's both more mundane and more unsettling. What if hydrogen cyanide isn't cargo good or bad, but exhaust? What if we're misreading a smoke trail as a message? That's where we go next. Picture this for a moment. You're close enough to 3I Atlas now that it fills most of your view, a dark, uneven shape laced with jets that flare and fade as it spins. In the silence of space, those jets are the only thing that tells you the object is alive to sunlight. But what if some of them aren't sunlight at all? What if we've been staring at the wrong kind of plume? Here's the more mundane and, in a strange way, more disturbing possibility. What if hydrogen cyanide isn't a toxin payload and isn't a prebiotic gift? What if it's just exhaust, not a message, not a weapon? Smoke. It sounds like a leap, so let's handle it carefully. The text is explicit that this idea is speculative and relies on chemistry we don't see in our own engines, at least not as a dominant signature. But it also lays out why the question is worth asking. Hydrogen cyanide can be made in high-temperature oxidative or catalytic environments. Burn hydrocarbons or amines in the presence of nitrogen, and nitriles like HCN can come out the other end as secondary products. In other words, you don't need a cyanide tank to get cyanide. You can get it as a byproduct of driving a hot reaction. That small point changes the story's geometry. HCN could be evidence of combustion-like chemistry happening inside or near the nucleus, rather than evidence of stored poison waiting to be delivered. Now, here's the first quiet hook. ALMA didn't just detect HCN. It mapped where the cyanide is coming from, and the map is awkward for a passive comet. Hydrogen cyanide appears to be venting from the nucleus itself, close to the core, while methanol is showing up far downstream more than about 258 kilometers away, where molecules usually break apart instead of assembling. If HCN was simply sublimating off sun-warmed ice, you'd expect it to be strongest on the sunward side, because that's where the heat is. Yet ALMA finds the opposite. Cyanide is depleted on the sunward side and enhanced on the anti-sunward side, or at least in directions that don't line up with solar illumination. So what this means is that the cyanide isn't behaving like a normal surface volatile. It's behaving like something leaving from specific ports, from specific locations, almost like nozzles. Of course, nature can make nozzles. Comet 67P showed asymmetric jets tied to cliffs, pits, and fractures. A rough surface can focus gas release into narrow beams, but the text points out that 3I Atlas's asymmetry is more pronounced, and the chemical split between coarse cyanide and wake methanol is not a neat match to our usual comet models. Now imagine the engineering thought experiment the text invites. A vehicle and alien spacecraft, Star Wars-like in broad silhouette but far sleeker in function, shedding low-mass exhaust to adjust attitude. Tiny nudges rather than dramatic burns. If you wanted to rotate or trim a trajectory at interstellar speed, you'd favour exhaust that is light, easy to accelerate, and good at transferring momentum per unit mass. Hydrogen cyanide fits that profile. In other words, cyanide could be reaction mass. Methanol could be something else entirely. Cargo stored separately, released through different vents, or produced in the wake through chemistry we talked about earlier. That's the dual-purpose mission picture. Propulsion and payload delivery in the same body. Here comes another soft recentering line. In other words, we might be misreading the roles of the molecules. We're asking what they mean for biology when we should first ask what they mean for mechanics. But if this is exhaust, where are the mechanical fingerprints? A chemically propelled interstellar vehicle would face real constraints. Mass budgets matter, reaction energetics matter, the fuel-to-cargo ratio matters. Those aren't hand-wavy issues, they're hard gates on feasibility. Still, the text reminds us they're not necessarily insurmountable for a technology more advanced than ours. So, what would we look for to tell exhaust from natural sublimation? One signature would be non-Keplerian accelerations, tiny deviations from the trajectory expected under gravity alone. Another would be light curve periodicities that don't match simple tumbling brightness variations that hint at controlled orientation or timed burns. Recurring jet patterns that trigger at regular intervals or under specific conditions would also be telling. And right now, we don't have confirmed reports of any of those. The orbit looks standard and hyperbolic. The brightness changes look consistent with an irregular tumbling natural body. The data, so far, don't force an engineered interpretation. But absence of evidence isn't evidence of absence. We haven't monitored 3I Atlas continuously. Subtle accelerations could hide in data gaps. Small attitude control could be below our detection threshold at this distance. So what this means is that the engine exhaust story can't be ruled out just because we don't see obvious thruster fireworks. Here's the tension that makes this part feel like a cold hallway. If hydrogen cyanide is exhaust and methanol is cargo, then we're looking at a machine. Or we're looking at nature doing such a convincing impression of a machine that we can't tell the difference yet. That uncertainty is the true weight of 3I Atlas. Not that it's a threat, and not that it's a saviour, but that a single number in a spectrum can tilt our intuition between a comet and a craft. And there's one more subtle hook. If HCN is exhaust, it implies a hot chemistry somewhere inside the object. Hot chemistry could also explain why methanol seems to appear where it shouldn't, far out in the plume. An engine-like process could be seeding reagents into the wake, or heating dust grains that catalyze methanol production downstream. The same mechanical picture that reassigns cyanide to exhaust opens extra pathways for methanol to surge. So we're left with a choice between two kinds of weird. Either 3I Atlas is an utterly natural interstellar comet with chemistry and venting that push beyond our standard models, or it is something that uses chemistry the way we use propellant, with cyanide as smoke and methanol as cargo. The universe hasn't told us which. It has only handed us a pattern and dared us to stay honest about what we don't know. Next, we have to confront the most stubborn piece of data in the whole story. The methanol output does not rise toward the sun the way normal comets do. It follows a power law that is too steep to sit comfortably in any simple sublimation model. The number is U5.2, and if cyanide is exhaust, that number gets even stranger. Let's go there in the next part. Picture this for a moment. You're watching a graph draw itself in real time, a smooth curve on a dark screen. On the horizontal axis is distance from the sun. On the vertical axis is how much methanol 3I Atlas is releasing. Most comets sketch something gentle here, a rise that makes intuitive sense as sunlight gets stronger. But this curve climbs like it's being pulled upward by something impatient. The line is steep enough that you feel it before you fully understand it. The slope is the issue. The methanol production follows a power law with heliocentric distance, roughly proportional to RH5.2 H.5.2 RH. That number is the stubborn knot in this whole story. In plain terms, As 3i Atlas halves its distance to the Sun, its methanol output doesn't just double or triple the way a normal volatile might. It spikes far more aggressively. It's a runaway behaviour, not a gradual thaw. In other words, it's not acting like a simple patch of ice warming up. Here's why that matters. For most known comets, production rates of common volatiles like water, CO or CO2 scale with distance in a range that reflects straightforward heating and sublimation. You get more sunlight, you get more gas. The relationship is strong, but not extreme. If you saw a curve this steep in a solar system comet, you'd assume you were missing an extra driver. So what could drive something like RH52 or KART-52 or 5.2 without leaving the realm of nature? The text lays out a few natural mechanisms, all plausible, all imperfect. One idea is layered methanol ice hidden beneath a crust. Picture a loaf of bread with a thick, dry outer shell. Early sunlight warms the surface, but the crust insulates what's underneath. Then, as heating penetrates deeper, a larger reservoir suddenly becomes thermally connected to space, and the outflow jumps. That could make production scale faster than expected over a narrow distance window. It's still sublimation, just delayed sublimation, like a vault door finally swinging open once the lock heats enough. Another natural route is clathrate release. Remember those ice cages we talked about earlier? Clathrates don't seep, they crack and dump. As the nucleus warms, you can cross a threshold where clathrate stability collapses. When that happens, methanol trapped in the cages can flood out in bursts. If those bursts line up with the distance trend, the overall curve looks steep even though what's really happening is a step-like sequence of releases. A third natural route is photochemical production, methanol being made near the surface or in the inner coma by UV-driven reactions. If the surface is rich in CO and hydrogen-bearing species, sunlight can push carbon into methanol more efficiently as intensity rises. And UV intensity doesn't scale linearly with distance, it scales with inverse square. But reaction efficiency can also increase with temperature, surface mobility, and catalytic activation. Stack those effects and you can build something steeper than ordinary sublimation. But here comes the quiet problem. Even with these stacked effects, RH5.2R's Phi 2.5.2 is hard to get. Nature has to work overtime. The models need either unusually favourable chemistry, a very specific interior structure, or both. So what this means is that we're not choosing between normal comet and aliens. We're choosing between exotic natural comet and something else that mimics comet physics while adding a hidden driver. This is where the engineering thought experiment re-enters, not as a conclusion, but as a way to check whether there's a simpler explanation for the steepness. If methanol is cargo rather than pure ice, you might not expect a gentle thermal curve at all. You might expect a controlled release that ramps with proximity to the Sun because proximity is the cue for emission phase. In that picture, distance is a timer. The closer you are, the more you vent. Not because sunlight forces you to, but because you've decided to. That's a chillingly clean way to get a steep power law. But it also assumes intent. And again, intent is the last thing the data can prove. You can fit a curve with a hand on a valve or with a fracture in ice. Both can make the math work. So let's keep the engineering picture grounded and testable. If the steep methanol rise is controlled, then it could show signs of modulation, periodic spikes unrelated to rotation, sudden throttling changes not predicted by solar heating, or a release pattern synchronized with orbital milestones rather than temperature alone. Those are things future spectra and light curves might catch. On the other hand, if the steepness is natural, it should correlate tightly with temperature and with the activation of known sublimation fronts. As 3i Atlas approaches the Sun, certain volatiles become unstable at predictable depths. If methanol tracks those thresholds, the curve might soften or break into segments that follow physical cliff edges rather than a smooth engineered ramp. We don't have enough data yet to see which path it's taking. We have a few early points and a slope that doesn't sit still in our intuition. Here's another way to feel the steepness without equations. Imagine warming a frozen can of soda. At first, nothing happens. The ice inside absorbs heat quietly. Then, once enough melts, pressure builds fast and the can starts to hiss. If the opening is narrow, the hiss can turn into a sharp jet. The output isn't proportional to how warm the room is at that exact second. It's proportional to the internal state crossing a threshold. A threshold can make the curve look like a cliff. That's a natural way to make steepness, but for it to match RH 5.2 and H 5.2 and H 5.12, the thresholds would have to be aligned in a precise way with distance. Not impossible, just demanding. And now we're back to the place this whole story keeps returning to. Demanding natural explanations are still natural explanations. They don't break rules, they just require an unusual origin story. So the steep methanol law doesn't prove engineering. It proves that 3I Atlas is not an average icy rock. It's carrying a thermal or chemical setup that we haven't catalogued well, because we've never had many interstellar objects to catalogue in the first place. In other words, part of what you're hearing in that steep slope might be our own ignorance. We only have 3 samples now. The third one is already telling us that interstellar comet could mean more than one kind of thing, but there's one more layer. If hydrogen cyanide truly is exhaust, even partially, then the steep methanol curve could be downstream chemistry driven by that exhaust. Hot products released near the nucleus can seed reaction chains in the plume, allowing methanol to be synthesized farther out where we don't expect it. That would explain why methanol seems to brighten in regions that are hundreds of kilometers from the core. You'd be looking at a chemical afterglow, not a simple leak. Again, natural or engineered? Both can light that afterglow. A natural nucleus with the right chemistry can do it. A machine with a hot exhaust can do it too. The curve doesn't choose for us. So what this means is the slope isn't a verdict. It's a constraint. It's a number that any explanation has to respect. And the moment you start respecting it, a bigger question opens up. Where did a body like this form? What kind of stellar nursery produces an object so rich in methanol, so structured in outflow, so steep in its response to sunlight? That's where we go next. We'll step backward in time, away from December 19th, and into whatever system 3I Atlas came from, and what its chemistry might be telling us about that birthplace. Picture this for a moment. You're not watching 3I Atlas anymore. You're rewinding the solar system like a film, then letting it fade into black and keeping the rewind going. Stars slide backward. The sun shrinks to a point. Around you, the Milky Way becomes a quiet spiral of nurseries and graveyards. Somewhere in that spiral, long before humans were anything more than a distant possibility, 3I Atlas formed. If we want to understand its chemistry, we have to think about the kind of place that could have built it. Interstellar objects don't form in a vacuum. They form in protoplanetary disks, cold, rotating pancakes of gas and dust around young stars. In those disks, temperature and radiation change with distance from the star and with time. You have warm inner regions where water struggles to freeze, and frigid outer regions where even carbon monoxide can become ice. Between them are snow lines, boundaries where certain molecules flip from gas to solid. Those boundaries matter because solids stick, grow, and become planetesimals. Methanol is one of the molecules that likes cold and darkness. It forms efficiently on dust grains when CO freezes out and hydrogen atoms can hop around on the surface. In many disks, methanol becomes a major ice component in the outer regions. But not all disks are the same. Some are more methanol rich than others depending on their chemistry and radiation environment. So what this means is that a methanol-heavy object already hints at an unusual birthplace, a disk where methanol ice was abundant and preserved. One pathway is simple inheritance. If 3I Atlas formed far out in a cold disk, it could have locked in a large methanol inventory the way a freezer locks in food. Then, when gravitational chaos tossed it out of its home system, interstellar cold would keep that chemistry stable for eons. By the time it wandered into ours, it would still be carrying the same molecular ratios it was born with. That's the most conservative story. And it has a quiet elegance. It says, the steep methanol behavior is not weird because the comet is weird. It's weird because we're sampling a disk we've never sampled before. There's another, slightly more intricate route. Disks can have localized chemical niches. A planet forming in the disk can carve gaps, trap dust, and create zones shielded from radiation. In those shadowed rings, certain molecules can build up dramatically. If 3I Atlas formed in one of those protected pockets, it could be methanol-rich, even compared with other bodies in its own system. In other words, its composition could be a fossil of a very particular neighbourhood in a very particular disk. Now fold hydrogen cyanide into the origin question. HCN often tracks nitrogen chemistry. It can be enhanced in disks that are rich in nitrogen-bearing organics and exposed to moderate UV irradiation. Some systems show strong nitrile chemistry in their outer disk layers. Again, not every system behaves the same. If 3I Atlas came from a nitrile active system, A methanol-HCN combo could be natural inheritance rather than engineered intent. The key point is that interstellar comet is not a single category. It's a sample from a population we barely know. We've been tempted to compare 3I Atlas to our own comets, the way you'd compare a foreign coin to the ones in your pocket. But foreign coins come from different mints, different histories. So do interstellar bodies. So what this means is that the most unsettling thing about 3I Atlas might be statistical rather than alien. We don't know what normal looks like out there yet. That brings us to isotope fingerprints. In principle, if you measure isotopic ratios, like deuterium to hydrogen, or carbon-13 to carbon-12, or oxygen-18 to oxygen-16, you can sometimes infer the kind of environment the object formed in. Those ratios are like accents. They don't tell you the whole story, but they can hint at where the speaker grew up. If future spectra find isotopic ratios unlike solar system values, that would strengthen the exotic birthplace explanation and help narrow down what kind of disk chemistry produced such a methanol-rich body. But if the isotopes look surprisingly solar-like, that would raise a different kind of eyebrow. It wouldn't prove anything on its own, but it would complicate the inheritance story. It would suggest a birthplace closer in chemistry to ours than we'd expect despite the behavioural weirdness. Either outcome teaches us something. Now zoom out to the broader implication that the text leans into gently, panspermia, but not as a sci-fi plot twist, as a natural statistical process. If interstellar objects frequently travel between systems, then they are a physical mechanism for exchanging organics. They're like slow-moving mail carriers for chemistry. Over cosmic time, even rare exchanges add up. A methanol-rich body passing through a young system could deliver carbon sources. HCN-carrying dust could deliver reactive nitrogen. Those materials could settle into cold oceans or subsurface niches and participate in chemistry for millions of years. In other words, systems don't evolve in total isolation. The galaxy is a leaky ecosystem. That doesn't mean life is intentionally seeded. It means that the raw ingredients for life are redistributed. Sometimes they land on worlds where nothing happens. Sometimes they land on worlds where something does. If 3I Atlas is natural, it becomes a demonstration of that leakiness. It tells us that other systems make organic cocktails at least as complex as ours. It tells us that methanol-heavy chemistry is not a local quirk. It might be a common galactic flavour, but the engineering story, even if you keep it at arm's length, hovers at the edge of this origin discussion too. Because a designed object could still mimic an inherited chemical accent. If someone wanted to travel quietly, leaving natural isotopic signatures might be a feature, not a bug. Again, we don't have evidence for that. It's just a reminder that origin clues cut both ways unless the dataset is rich. So the most honest place to stand right now is this. 3I Atlas looks like a messenger from a different disk. A disk we haven't met before. Methanol abundance and steep response might be signatures of a cold, chemically fertile birthplace. HCN might be part of that same fertility, and our job is to keep measuring until the fingerprints sharpen, because the moment they sharpen, the story forks. If the fingerprints point clearly to an exotic natural disk, then 3I Atlas becomes the first true sample of another star's outer chemistry, and the steep methanol curve becomes a window into how diverse comet birthplaces can be. If the fingerprints remain weird in ways that don't fit disk chemistry, then the engineering corridor stays open a little longer. Either way, there's another piece we need to weigh, the one that feels most human. The text explores whether the methanol-HCN mix could be interpreted as deliberate terraforming or biological intervention cocktail. It's a speculative idea, and it needs to be handled without melodrama, because it sits right at the boundary between chemistry and intention. That's where we go next. Picture this for a moment. You're floating above an icy world that has never seen a sunrise in any familiar sense. The surface is a pale shell, cracked and ancient, and beneath it an ocean rolls in permanent darkness. Around you, the solar system feels wide and mostly quiet. This is the kind of place where chemistry can sleep for ages, and where a small push could change everything. By now, you can feel how easily the story about 3I Atlas can slide between two moods. In one mood, its chemistry is a natural gift. In the other, a deliberate act. The text steps carefully into a more daring thought experiment here, not to declare anything, but to test how far the data could stretch without tearing. What if that methanol-HCN mix is not random at all? What if it's a functional cocktail? There are two ways to imagine that cocktail, and they're almost opposites. The first is gentle in intent. Methanol, in the right environment, can feed chemical networks that lead toward more complex organics. Hydrogen cyanide, while toxic in high doses, is also a potent precursor in classic prebiotic pathways. If you delivered both into a cold, protected ocean, a Europa-like ocean, you could be nudging chemistry along very specific routes. You wouldn't be dropping finished life. You'd be increasing the odds that life could emerge. In other words, not planting a tree, but enriching the soil. The second way to imagine the cocktail is darker. Hydrogen cyanide can suppress biology. It interferes with respiration, meaning it can quiet or reset a biosphere if the doses are right and the delivery is focused. If a world already hosts primitive life, a cyanide-rich injection could prune it back, creating ecological space for something else to arrive later. In that framing, methanol could be a stored carbon reserve for a follow-up wave of chemistry. That's the sedation picture, not necessarily permanent sterilization, more like knocking a system down a rung. Now, before your brain locks onto either of those, we need to be serious about scale and about what the data actually warrant. The text itself is clear that this is speculation. It's a way to see whether the chemistry could be interpreted as deliberate. But chemistry alone can't prove intent. It can only show capability. So what this means is we're asking, could it function that way? Not, is it being used that way? Let's stress test the gentle version first. If an interstellar object simply vents methanol and HCN into space, most of it disperses and becomes irrelevant. The only way it matters for seeding is if some of that material gets deposited into a receptive environment. A subsurface ocean under ice is receptive because it's shielded from harsh radiation, stable over long timescales, and not already saturated with complex life. If even a small fraction of organics reach that ocean through cracks, plumes, or impact delivery, they can participate in chemistry for millions of years. That's why icy moons keep showing up in this story. They are places where low probability delivery can still lead to high impact outcomes over geological time. Methanol is useful there because it's a flexible carbon source. In high-pressure oceans, methanol can participate in redox reactions and feed chemosynthetic metabolism if any exists. Even prebiotic systems can use it as a stepping stone. HCN complements that by providing nitrogen in a reactive form, making it easier to form amino acids and nuclear-base-like structures under the right catalytic conditions. So the gentle cocktail is chemically coherent. It doesn't need science fiction to work. It only needs delivery into the right setting. Now stress test the darker version. To suppress a biosphere, you need enough hydrogen cyanide to reach biologically meaningful concentrations in the environment that life occupies. For Earth-like surface life, that would require targeted atmospheric injection at high doses. For subsurface ocean life, it would require direct delivery into the ocean or into connected conduits. Passive outgassing from a distant flyby does not do that. In other words, a serial killer cocktail only makes sense with control and precision. We don't see evidence of that precision. We don't see shaped impacts. We don't see deliberate braking. We don't see steering toward known habitable niches. What we see is an object following a natural-looking hyperbolic path and venting in jets that could still be explained by sunlight and internal structure. So if you keep the darker picture alive at all, it's only as a remote possibility, one that would require much more evidence than we have. The text is trying to hold both frames in view without letting either pretend to be confirmed. That's the right posture. Because in astronomy, the danger isn't usually being too imaginative. The danger is being imaginative without being falsifiable. So what would falsify deliberate cocktails? The easiest kind of falsifier is correlation with mission-like behavior. If outgassing ramps at distances that align with strategic orbital nodes rather than thermal thresholds, if the composition changes in a way that suggests staged release, if the jets appear tuned, turning on and off in synchronized repeatable sequences that don't match a tumbling icy rock, those are the kinds of patterns you can look for without needing to read anyone's mind. But until those patterns show up, the safest reading is still the natural one. Methanol and HCN are common cometary products, and their abundance in 3I Atlas may be telling us more about alien disks than alien intent. Still, there's an emotional reason this section matters. It forces us to notice that chemistry is ambivalent. A molecule that can help build RNA can also shut down respiration. A molecule that can feed chemosynthesis can also poison a nervous system. The universe doesn't label tools as good or bad, it just makes tools. In other words, the same interstellar courier could look like a gardener to one world and a killer to another, depending on their starting conditions. That's not drama, that's thermodynamics, chemistry and chance. As December 19th approaches, we're going to get more numbers, more ratios, better maps, maybe isotopes. Those numbers will either make the cocktail look more like a natural chain of disk chemistry, or they'll keep the interpretive tension high, and there's a new tension coming right behind them. The text shifts now into a bigger question about detection itself, about how we decide whether something is natural when we're only reading light and chemistry from afar. It brings artificial intelligence into the frame, not as a gimmick, but as a tool that can sometimes see patterns we miss. That's where we go next. Picture this for a moment. You're in a quiet lab late at night, the lights low, the room humming softly with cooling fans. On one monitor is the spectrum of 3i Atlas. On another is a star's light curve, a thin, jagged line showing tiny flickers in brightness over time. To the human eye, that line looks like noise. To a machine trained on 1,000,000 stars, it can look like a signature. The text makes a sideways move here into something that sounds futuristic but is already ordinary science, using artificial intelligence to read chemistry and structure from light. Not because AI is magic, but because the patterns we're searching for in objects like 3i Atlas are subtle, and subtlety is where machines can help. Think about what we're really trying to decide. We're not asking whether methanol or hydrogen cyanide exist. We're asking whether the way they behave fits a natural comet model, or whether there's an extra driver hiding in the system. That's a pattern recognition problem. And pattern recognition is what neural networks are built for. In December 2025, AI models are already doing things that used to take teams of astronomers months. They scan vast catalogues of stellar brightness changes and infer things about stellar surfaces, rotation, magnetic activity, even the chemical composition of atmospheres. A human can read one spectrum well. A model can read 100,000 and learn what normal looks like across different environments. So what this means is that AI gives us a richer baseline. It helps tell us whether 3i Atlas is truly outside the natural distribution, or whether it only feels strange because our sample size is tiny. There's an eerie comfort in that. Because the more normal we can make nature by expanding our reference set, the less space there is for our imagination to run ahead of the data. But AI also does the opposite. Sometimes it spots anomalies humans overlook, a faint periodicity, a tiny mismatch between expected and observed decay rates, a multidimensional cluster of properties that doesn't line up with any known family of objects. When that happens, AI doesn't tell you why something is odd. It just tells you that it is. In other words, it can become an early warning system for, this doesn't belong in the usual bins. So, how does that apply to 3i Atlas? Imagine feeding an AI the spectra and outflow maps of every comet we've ever observed, plus simulated comets formed under a wide range of disk conditions. The model learns correlations we already know, how water, CO, CO2, methanol, and nitriles tend to co-vary with distance and temperature. It also learns correlations we don't articulate well, subtle ties between jet symmetry, rotation state, and chemical gradients that emerge only in big data. Then you hand it 3i Atlas and ask, where does this thing sit in that learned space? If it lands inside a known cloud, then the steep methanol curve and the HCN asymmetry may just be rare but natural outcomes. If it lands far outside, then we have a genuine anomaly to chase with physics, not with vibes. The text frames this as an intelligence test, and it's a good phrase if you hear it the right way. Not a test of whether aliens are real, a test of whether we're capable of reading an unfamiliar object without forcing it into our existing story templates, because that forcing is the real trap. Humans are excellent at inventing meaning. We see a split chemistry and we sketch gardeners and killers. We see symmetry and we sketch nozzles. We see a steep curve and we sketch intention. Those sketches are useful as hypotheses, but they can also become mental gravity wells. Once you fall into a story, everything becomes evidence for it. AI can help loosen that grip because it doesn't care which story is emotionally satisfying. It cares about likelihood and clustering. It won't stop us from being imaginative, but it can keep us honest about whether imagination is being dragged by data or by narrative hunger. So what this means is that the best role for AI here is not to decide natural versus engineered. It's to tell us what's statistically abnormal given everything else we know. There's another layer to this, and it's subtle. If you assume a sufficiently advanced civilization could hide in plain sight, then the hardest thing for us isn't spotting technology. It's spotting technology that's intentionally camouflaged as nature. In that case, you don't look for obvious spaceship signs. You look for the tiniest, most persistent deviations from natural ensembles. That's a job AI is unusually suited for, because camouflage works best against human expectation. It works less well against brute statistical comparison across huge datasets. But again, we're still dealing with a thin dataset. 2 previous interstellar objects are not enough to define a population. Our comet catalogue is solar system biased. Our simulations rely on disk chemistry models that can be wrong in details. AI can only be as good as the baseline we feed it. In other words, AI isn't a judge, it's a flashlight. And it's especially useful now because 3i Atlas is moving fast. The observation window is narrow. Every week closer to December 19th tightens the geometry and changes the thermal state. If there are mission-like stages in its behaviour, if jets turn on in a sequence, if chemistry shifts in a way that doesn't line up with heating, those changes could be fleeting. A neural network that watches continuously could spot patterns that a human reviewing data later might miss. So we're in a strange moment where the oldest scientific practice, careful observation, is being fused with one of the newest tools, machine learning, to read something that may be older than the sun. That doesn't make the story less human, it makes it more so. We're extending our senses, and as we extend them, another question sharpens. Suppose AI and spectroscopy together confirm that certain aspects of 3i Atlas are anomalous. What then? What does anomalous mean in a universe that can produce exotic natural objects we've never seen? It means we go deeper into physics. We test thermal models, we test clathrate stability, we test photochemical pathways, we test whether plasma focusing can reproduce the wake geometry. We add knobs to our natural explanations until they either fit or fail. Only if they fail cleanly do we even start leaning on extraordinary interpretations. That's the scientific rhythm. Mystery, model, test. Reduce the mystery, then face what's left. So what this means is that the intelligence test isn't about whether 3i Atlas is a spacecraft. It's about whether the combination of humans and machines can resist premature certainty and keep listening long enough to learn what this object truly is. And there's one more whisper waiting behind that test. The text turns toward a deeper, almost philosophical but still physical frontier, whether space-time itself, the medium this object crosses, has hidden structure, and whether that structure might help explain the filamentary behaviour we're seeing near pulsar environments and in the wake of 3i Atlas. That sounds like a leap. But it's the next rung on this ladder. Picture this for a moment. You're far from any planet now, drifting in a region where the solar wind thins and the sky feels less like a dome and more like a depth. Ahead, a pulsar's glow cuts through dust like a lighthouse through fog, and along that beam you can almost see the scaffolding of the galaxy. Long, faint filaments that shouldn't be there if space were perfectly smooth. The text ends by widening the lens. It treats 3i Atlas not only as a chemical puzzle, but as a probe moving through a medium we still don't fully understand. Because if there's one theme that keeps repeating, it's this. Odd behaviour can come from an odd object, or from an odd environment, and sometimes the environment is the strangest part of all. Start with the idea of smoothness. In classical physics, space-time is continuous. If you zoom in far enough, you expect more detail, not a new kind of grain. But some approaches to quantum gravity suggest that, at extremely small scales, space-time might have structure. Not a literal lattice you could photograph, but a statistical texture that can influence how fields and particles propagate. In other words, the vacuum might not be perfectly empty in the way our intuition wants it to be. Most of the time, that texture would be invisible. But in extreme environments like near pulsars and their nebulae, we sometimes see phenomena that make you wonder whether the medium itself is guiding matter. The text points to the ordered, thread-like radio structures observed in certain pulsar wind nebulae, filaments that align, persist, and appear more coherent than simple turbulence models predict. Those filaments are not proof of new physics, but they're reminders that magnetic fields, plasma instabilities, and maybe deeper microstructure can organize space into pathways. Pathways matter because they move things, They can shepherd dust, shape tails, and focus outflows into narrow lanes. So what this means is that a wake like 3-eye atlases might be less like smoke in still air, and more like dye dropped into a river system you can't see. If the coma produces charged nanograins, and the data suggest it does, those grains can couple to magnetic fields and drift along field-aligned filaments. Even neutral molecules can travel with them through sticking and collisions. The result is not a perfectly spreading sphere. It's a lopsided plume with the potential for bright, focused threads far downstream. That's important because it offers a natural way to get some of the organised behaviour we keep bumping into. You don't need an engine to make a filament if the heliosphere itself can build one. At the same time, the text never lets you forget the counterweight. If 3-eye Atlas were an engineered interstellar warship or spacecraft using the medium as camouflage, venting in ways that ride magnetic lanes and mimic natural tails, then our environment-based explanations could be exactly what a designer would exploit. In other words, the richer the natural medium is, the easier it is for technology to hide inside it. That tension is the quiet final chord. Nature can imitate design, design can imitate nature, and the medium can blur the boundary. But before we drift too far into abstract physics, the text brings us back to the ground with something wonderfully concrete: chemistry in a lab. A recent experimental result shows that methanol, under radiation and catalytic conditions similar to icy bodies, can be driven into more complex prebiotic precursors, including molecules that sit 1 or 2 steps away from RNA building pathways. The key point isn't that methanol guarantees life. It doesn't. The point is that methanol is not chemically inert baggage, it's active potential. So what this means is that if methanol from 3-eye Atlas settles into a stable, protected niche, say a subsurface ocean or a shadowed porous crust, it can participate in real chemistry, not just float by as a curiosity. It becomes one more way that the galaxy shares its ingredients. Put the pieces together and you get the final landscape. On one side is the sober, natural story. 3-eye Atlas is an interstellar body born in a methanol-rich, nitrile-active disk. Its steep methanol power law comes from threshold release, clathrates, or UV-driven surface reactions. Its HCN asymmetry comes from heterogeneous vents, and the way plasma and magnetic structure sculpt the wake. December 19th is simply a close pass that happens to align with Earth's orbit, not a deliberate approach. In that reading, the object is strange but not intentional, a messenger of chemical diversity. On the other side is the minimal engineered story. 3-eye Atlas could be a vehicle using HCN-rich exhaust for subtle control and methanol as staged cargo. Its release ramps with distance, because distance is a mission clock. Its vents look symmetric, because they're functional ports. Its wake might ride heliospheric filaments because an advanced craft would naturally take advantage of the medium. And Earth is not necessarily the destination, just a system to sample on the way to quieter icy oceans. Both stories are physically possible, only one is likely. But likelihood isn't a feeling you can extract from a single spectrum, it's something that sharpens as data accumulate. And that brings us back to December 19th, 2025, not as a punchline, but as a pivot. The closer 3-eye Atlas gets, the more it will either settle into a recognisable natural family, or keep carving out its own category. Either way, we'll learn something fundamental: what other systems build, how common organic-rich wanderers might be, and how porous the border between stars really is. There's a calm kind of awe in that, not the loud fireworks kind, the kind you feel when you realise your home system is not a closed room. It's a doorway and hallway of doorways. So tonight, or any night you let this story roll on in the dark, you don't have to decide whether 3-eye Atlas is a gardener or a killer, a comet or a craft. You only have to hold the question gently and let the universe answer in its own slow language, because the truth is already on its way. And whatever it turns out to be, it will arrive not as a shout but as a few more quiet lines on a graph, lines that once you've seen them, you can never unsee.